Welcome back. Today I would like to discuss about the analysis of common gate amplifier. In previous lecture we have seen that two MOSFET amplifiers like common source amplifier with source resistor and common drain amplifier also. Now in this class I would like to discuss the common gate amplifier. See the diagram. The MOSFET is in common base, that is not common base, common gate. The gate is at the ground potential, whereas input to the source terminal and output we are considering from the drain. And CC1 and CC2 are the coupling capacitors at input and output. Okay, you know the purpose of coupling capacitors are to allow only AC components but blocks the DC components. So for the analysis, you have to convert the MOS transistor into equivalent circuit. Okay, so this is the equivalent circuit for the amplifier, totally small signal equivalent circuit. So for deriving the small signal equivalent circuit, what we have to do, MOS transistor is replaced with the equivalent circuit. DC sources must be put 0, that is acts as a short circuit, so that the equivalent circuit is like this, right? Input is at the source, output from the drain terminal, and as per the equivalent circuits, between drain and source there is a current source GM-VGS, and in between source to gate no component is presented, that's why it is treated as a open circuit. The rest of the components from the amplifier circuit, right? Now let us see the analysis. First of all, as usual, the voltage gain derivation. For that, voltage gain means output voltage divided by input voltage. From the circuit, the output voltage is the drop across R0 parallel RL is the output voltage. Okay, but how much is the current? GM-VGS. Therefore V0 equal to, V0 is minus GM-VGS into RD parallel RL. Okay, but the VGS is derived from the input, that is VGS equal to VGS. How can you write the VGS? The VGS is at the input side, VI equal to the drop across RSI, plus VGS. Okay, but with the polarities are such a way that it comes like VI is II RSI minus VGS. Okay, and here the current II is minus GM-VGS, right? The current II is minus GM-VGS. See this diagram, II is minus GM-VGS. By substituting that value instead of II, the VI becomes like this, and from that if you calculate VGS, it comes like minus VI divided by 1 plus GM RSI. Now substitute this VGS in the V0 equation. Substitute this VGS in the V0. Therefore, the voltage gain V0 divided by VI equal to GM into RD parallel RL divided by 1 plus GM RSI. Clear? Next, coming to input. Okay, current gain also derived here since it is a common gate. Okay. Okay, current gain means output current divided by input current, that is I0 divided by I. Okay, so therefore first of all I am going to see what is I0 current. Okay, I0 current. So the I0 current is, if you observe here, this is a parallel circuit. For this parallel circuit, the supply current is minus GM-VGS. Therefore the current in RL is applied by, so this supply current minus GM-VGS into RD divided by RD plus RL. Okay, so like that you can directly write the equation for I naught, right? Then you also see here the VGS. Okay, from the input side, from the you have to substitute the VGS, but in terms of current, right? Now to derive this VGS, represent the voltage, I mean VI voltage series resistor into current source parallel resistor. That is the VI in series resistor is the Thevenin model. Now convert into Norton model. Okay, in Norton model, what we have a current source parallel to its internal resistance. Okay, so that's why at the input side, the voltage source is converted into current source like this. Okay, now the current source magnitude is IA and its internal resistance is RS connected in parallel. Okay, so therefore from the input the IA current equal to the IA current is, or writing the KCL equation at the source node, that is II plus VGS divided by RSI plus GM VGS equal to 0. Therefore VGS equal to minus II into RSI divided by 1 plus GM RSI. Okay, from this KCL equation you need to get the VGS. Now substitute this VGS in the I naught equation. Substitute this VGS in the I naught. Therefore AI equal to I naught divided by II into that equal to RT divided by RD plus RL into GM RS divided by 1 plus GM RSI. Okay, are you clear? First of all, you have to calculate the I naught value, but the I naught in terms of VGS you can get, and you have to derive the VGS from the input equation, the input KCL equation, and substituting that VGS in the I naught you can get the current gain, right? Suppose if RD is very high compared to the RL, and GM, the product of GM and RSI is far greater than 1, then if you observe the above equation, all are cancelled and it becomes unity. You know, in the current gain in CG configuration is unity. Okay, like alpha in case of CB configuration of BJT. Okay, that is alpha is almost nearer to the unity. Similarly here also in common gate case the current gain we see that it is almost equal to unity, right? Next, coming to input impedance. The input impedance is see the circuit, the input impedance Ri is input impedance. This is the place where you need to observe the Ri value. So the Ri equal to minus VGS divided by II. Okay, Ri you can get, resistance is the ratio of voltage divided by current, that is minus VGS divided by II. But II is, you know, minus GM VGS. Substituting that one, Ri you can get as 1 by GM. Ri is 1 by GM. And coming to output resistance, you know, the condition is the independent sources should be 0. Okay, therefore Vs is 0. Vs means Vi. Okay, Vi becomes 0. When Vi is 0, it is like a short circuit. Okay, it is a short circuit, and that is when it becomes a short circuit. The VGS, the GM VGS also becomes 0. Therefore, it acts as a open circuit. Hence, the output resistance is the parallel combination of RD and RL. Okay, if you look at the output resistance as per circuit, it is equal to RD. But if you see from this point, it is RD parallel RL. Like that, the output resistance is derived. Thank you.